Bismillah ar-Rahman ar-Rahim. On this video, we are going to discuss fixed point arithmetic, okay? Fixed point arithmetic, or numbers basically, and their arithmetic. So when we say fixed point, we mean numbers that have integer and fraction part, okay? Fraction part. So basically, this is exactly what we mean, integer and fractional part. The number has integer and fractional part. As many of you have studied in COE 301, there is what we call the IEEE 754, yeah? 754, which implements floating point numbers. Floating point numbers are different from fixed point numbers, okay? And actually, they offer greater precision and range of values, however, at the expense of more complex circuits, okay? Fixed point arithmetic, on the other hand, is much simpler, much more simple, or much simpler than the floating point circuits, okay? Anyway, this is at the bottom of the slide, you can see an example of a fixed point number here, okay, that is characterized by the width W and the scale S, okay? The scale basically tells you how many fractional bits the number has, okay? And the width tells you how many bits, the total number of bits the number has. This will tell you exactly where the binary point is fixed at. And this is why the number system here, or these numbers are called fixed point, because once you choose your scale parameter and width, you know exactly where your binary point is. So we have an imaginary binary point here. So this is the fraction, and this is the integer for this example. So the integer is basically what? It's basically 3 plus 8, which is 11. You just convert binary to decimal, okay? 11 in decimal, and the integer, the fractional part is basically the integer part. Just convert it to integer and then divide by 2 to the power negative scale, basically, to get the exact value of the fraction. So the value here is, again, it is 11. So this is going to be plus 11 divided by 2 to the 6, or multiplied by 2 to the minus 6, okay? This will of course, be converted to a fraction, simple fraction. But again, you are limited with respect to the number of bits, okay? The number of bits in the fraction is not more than 6 bits, okay? 6 bits. And this 11 over 2 to the 6 and decimal is exactly 11 point. I just punched it in the calculator, and it's 171875, okay? This is exactly the decimal number that corresponds to this binary number, okay? However, in the computer memory, or in registers, this fixed point number is stored as a string of bits. So this string of bits is nothing but an integer, okay? So it's stored as an integer, and its value is going to be, so let's say that you have A, okay, as a fixed point number, okay? Its value is going to be the integer part, the integer, this is this bit as integer, multiplied by 2 to the negative scale, okay? Multiplied by 2, so divided by 2 to the scale, all right? Because you need to, you have to shift the number to the right, okay, to the right by s. So you multiply by 2 to the negative s. So this is exactly the value. So internally, the number is stored as I, as an integer, but its value is going to be I into I multiplied by 2 to the negative s. So if I give you the fractional value of a number, or the fixed point value of a number, then you should be able to get the integer representation by just multiplying the two sides by 2 to the s. So basically, I equals 2 to the s into f, okay, into f. So basically, if you want to convert a fraction, a decimal fraction, for example, let's say that you have a fraction 5.5, and you'd like to represent it using, for example, this exact fixed point notation, then you just all you have to do is to multiply it by 2 to the 6, okay, which s is 6 here. So multiply that by 2 to the 6, okay, and then get rid of the rest of the fractions, convert everything to binary, and then this is going to be the integer representation of your number, okay, integer representation of your number. All right, I'm a little bit ahead of myself here, but that's fine, okay. So again, the main two parameters for fixed point representation are W and S, the width and the scale. Okay, the width and the scale tells you exactly what is the range of your number, okay, fixed point number, and what is the precision. Okay, what is the precision? Basically, the precision is always going to be 2 to the negative s. Okay, 2 to the negative s. So each time you increment your integer by 1, you're incrementing the value of the fixed point number by 2 to the negative s. All right. Now think about this, because this is very delicate and very subtle. Okay. So this is exactly delta, the error. Okay, the error at which, or the increment at which we move from one fixed point number to the next. Okay, to the next fixed point number. Okay. Right. So usually we use this notation here, fixed, to indicate the format here, shorthand notation, fixed, and then we give it W and S. Yeah, like for example, we say fixed, for example, 32, 12. This means that your fixed point number. So if I say, for example, your A is a fixed point number that has 32 bits, and 12 bits of these 32 bits are fraction bits. Okay, so this is exactly what do we mean by this notation. Okay, all right. So what are the advantages again of fixed point numbers? Basically, efficiency. You can perform addition and subtraction exactly as integer and addition, addition and subtraction. Division and multiplication, you just need to perform integer division and integer multiplication in order to get the result, rather than doing floating point, right, like the floating point unit. Okay, floating point division or multiplication. What about the disadvantages? The disadvantages, we have what we call limited range, because once you decide on the number of bits, that's it. You cannot exceed these bits, and possibly this will affect also the precision. Okay, the precision of your numbers. Okay, of course, this is in comparison to floating point representation. Also, if you want to manage overflow, then this requires a little bit of thinking, okay, because that's a very delicate, especially for multiplication and division. Okay. Okay, so Addition and subtraction. How do we do addition and subtraction? It's straightforward. So if we want to do addition, for example, of 1.110, this number here is fixed 5 and 2. And we would like to add that to 0, 0 point. Maybe I'll add 1 here, okay, to make it. Sorry, I just this was wrong. The 2 was wrong. It was 3, okay, but then I incremented it to 4, and then this is going to be the total width is 6, so 6, 4. Okay, so let's add, for example, 0, 0, 1, and then 0. Okay, I don't want to overflow, so let's add some more bits here, and change this one to 1. Okay. Oh, I don't need this 0 here. Okay. So this is addition. Then you just perform the addition as if these were just binary numbers. Okay. Let me just scooch this over to the right, a little bit below here. Okay. And then just perform that. So I changed, by the way, I changed the total width of the number is 8 now. It's 8. So let me just fix that. And you have only 4 fractional bits. It's very important for addition and subtraction to be successful that all the operands belong to the same fixed point notation, meaning that their fixed point, what we call binary point, is aligned, perfectly aligned. So 1 plus 1 is 0 with a carry of 1, and then 1 plus 0 plus 1 is 0 with a carry of 1, and then 0 with a carry of 1, and then again 0 with a carry of 1. Okay, just ignore the altogether. Ignore the point. Just put it exactly in its same location. Okay, then 1 plus 1 plus 0 is 0 with a carry of 1. And then 1 plus 1 plus, again, 0. There's an implied 0 here. It's 0 with a carry of 1. And then 1 plus 0 is 1. Okay? And then 1 plus 0 is 1. So this is the final result of the addition. So it's basically the integer that is resulting is going to be 1 0 1 1 0 0 0 0 0 0 without, of course, the binary point. Okay. And then to get the fixed point representation or fixed point value of this, we just need to divide this by 2 to the minus 4, or multiply it by 2 to the minus 4, or divide it by 2 to the 4. Similarly, subtraction can be done in the same way. Now for multiplication and division, this is a little bit more involved. So let us assume that we have A, okay, which is basically in floating point representation, f sub A. Okay, let me just move on to the next page, because this is actually more requires a little bit of more attention here. Okay, so let me use black color here. So the fixed point value of A is basically the integer bits of A multiplied by, as we saw in the first slide, okay, we derived that, 2 to the negative S, okay, assuming you have a scale of S and the width that is not mentioned here of W, okay? So W and S are your basically parameters. Okay, and I would like to multiply that by B, which has the fractional value or the fixed point value of I, the integer value of B, okay, multiplied by 2 to the negative S, okay? Now, my multiplication result, which is FC, okay, is going to be some integer, okay, value multiplied by, again, the same scale, okay, minus 2 to the times 2 to the minus S. But I know that this is what? This is nothing but the fixed point representation of A multiplied by the fixed point representation of B. All right. Then I will expand this to be this, and this to be this. Okay, so this equals IA. My whole exercise here is to derive what? Is to derive IC. Okay, so I want to find out what is IC. All right. So first of all, let me just continue my pursuit here. So this is 2 to the negative s multiplied by I. This is FB now. IB multiplied by 2 to the negative s. Okay, and this equals IA into IB into 2 to the negative 2s. Okay. So what does this equal to? This equals FC, which is what? FC, which is IC into 2 to the negative s. This equals FC, right? So again, I just substituted FC by its value here. So I can now divide by 2 to the s, negative s, both sides. So IC now, the integer value of C equals IA into IB. If you divide by 2 to the negative s, you get 2 by 2 to the negative 2s becomes negative s. Okay, and this is exactly how you get the bits of the fixed point number C. Okay, you just multiply the integer. This is integer multiplication. Okay, integer multiplication, IA of IB times IB. Then you shift to the right by S bit. Okay, this is exactly how you get the results. The integer bits of C. Okay. Then you know that the value of C is going to be the integer value of C multiplied by 2 to the negative s. Okay, to get the value here. Okay. Okay, what about the division now? Let me add one more page here for the division. So for the division, we have, again, we have FA, which is A, IA into 2 to the negative s. And we have FB, which is IB into 2 to the negative s. And I would like to calculate FC, which equals, actually not, I would like to calculate IC, which is related to FC by this formula here, 2 to the negative s. Okay, so my IC is going to be what? FC into 2 to the s, right? 2 to the s, right? So I can expand FC now, which is supposed to be the division result, right? The division. So FC is nothing but FA divided by FB, right? The integer, this is the fixed point division. So I can substitute FC here to get in terms of IA and IB. So IC equals FA, which is what? IA into 2 to the negative s divided by IB into 2 to the negative s multiplied by 2 to the s. So this cancels with this, and you are left with IA multiplied by 2 to the s divided by IB. Okay, so in order to calculate the bits of C, which is the result of the division, you shift IA to the right by S bit, and then integer divide by IB. Okay? So exactly this is how we can get it. So IC, we can get the division result, okay, by and then the value, the fixed point value of C is going to be IC again multiplied by 2 to the negative s. Okay. I hope it's clearer now, because I think in the lecture last time I didn't actually explain it this way. Okay, what about real-world applications of floating fixed point arithmetic or fixed point numbers? Okay, so basically, in embedded systems as well as digital signal processing, fixed point arithmetic plays a central role. Okay, because usually embedded systems usually have very limited resources, and maybe a floating point unit is not really a luxury that you can afford. So basically, you have to implement the arithmetic operations as fixed point, okay, fixed point operations in either embedded systems or digital signal processors. Usually, as I said, microcontrollers does not come with floating point units, which are very expensive. Okay, they are just processors or co-processors. All right, so they don't come with that. So you have to implement fixed point arithmetic in order to compensate for dealing with fractions. Okay, that's all for fixed point numbers and arithmetic. See you in the next lecture.